Alright, welcome back. Thanks for tuning in for another physics lesson with Mr. M. Today we're going to be tackling the subject of Newton's universal law of gravitation. Okay? Basically, with Newton's universal law of gravitation, basically what it's stating is that all objects attract each other with a force of gravitational attraction. Okay, and we're specifically going to be taking a look at an equation in which we can actually solve the force between two different objects. Okay, but what's really cool is the fact that even you are exerting some type of gravitational attraction to all of the objects in the room. That's just so small that you don't feel it, and the objects obviously don't feel it as well. Okay. This attraction, this universal law of gravitation attraction is, as we're going to see, directly proportional to the product of the masses of the two objects and inversely proportional to the square of the distance between them. So what this means is, as the mass of those two objects increase, the force of the attraction will also increase, and vice versa. If the mass of our objects decrease, then the force of attraction will also decrease. What it also says is, as the distance between the objects becomes further away, the force of attraction will decrease by a factor of the square of the distance. Vice versa, if we bring those objects together, meaning closer, the force of attraction will actually increase. And here's our equation for the universal law of gravitation. It's denoted with a capital F and a subscript capital G. And we also see that capital G within the equation. And that capital G is called the universal constant. And it has this value, 6.67 times 10 to the negative 11th. And that's a constant value, so you can always plug that value in for capital G. We also have M1 and M2 on the top of our equation. Those are denoting our two objects that we are going to be calculating the force of gravitation between. And then on the bottom of our equation, we've got our radius squared, and that's where we're going to plug in the distance between those two objects. If we were to make a graph out of this equation, our graph, as you can see, is going to end up taking the form of a parabola. Basically what this graph is showing us is that if our distance is very far away, then our force is very little. Okay? And if our distance is very close, then our force is going to be very strong. Okay? And as we can see with the Earth, the closer we are to the Earth, the more we're going to feel that force of gravitation. But the further we get away, the less that force is going to be attracting us as objects. Okay? So let's take a look at how we can utilize this equation. Okay, and so our example here is we want to be able to calculate the gravitational force between two 15-kilogram bowling balls whose centers are 35 meters apart. One of the things that I always like to do with my students is make sure that we get all of the information out of the problem. Okay, and so in this case, we have two 15-kilogram bowling balls. So those are going to be our two objects, and we also know that they are 35 meters apart. We can also tell by the problem is we're trying to solve for the gravitational force. Okay, and so with that, what I always like to do as well is to list my known values and my unknown values. Okay, and first of all, I know the mass of my first object is 15 kilograms. I know the mass of my second object, which is, once again, 15 kilograms. I know the radius of the distance between my objects, which is my 35 meters. And I know that the gravitational constant is always going to be 6.67 times 10 to the negative 11th power. So those are my known values. my unknown value, the value that I'm solving for, is my force, my gravitational force. And so that's what we are going to be solving for in this episode. Okay, and one of the main things is, well, we want to have that equation with us. We want to be taking a look at that equation. So once again, our force is our capital G times the mass of our first object multiplied by the mass of our second object, all over our radius squared. Okay, and our goal here is we're gonna basically plug in all of these values into our equation. All right, so here's what that's gonna look like. The force is equal to our constant 6.67 times 10 to the negative 11th. Multiply that by our two objects, which are 15 kilograms each. And we're going to divide that all by our radius, which is going to be 35 meters squared. Okay? When we plug all of that in, we are going to get an answer of 1.50 times 10 to the negative 8th on top, and on bottom we are going to get 1,225 meters. Okay. Once we simplify this fraction, our value is going to come out to be quite small. Okay, our answer here is going to be 1.23 times 10 to the negative 11th. And we know that this is a force, so our force has our units in newtons. Okay, and so there we have it. And as I mentioned, this value makes sense because it's so small, because our objects are not very massive at all, and the distance is very far away. So it would make sense that our value here is going to be very, very, very small. Okay, you may be using this equation to calculate the gravitational forces between maybe the Earth and the Sun, or maybe two planets. In those cases, because the planets are so massive, you're going to get a force that's, going to be pretty prevalent. Okay? Alright, so hopefully this video was helpful for you in being able to solve for Newton's universal law of gravitation. Thank you so much.